All right, so hi everyone, and welcome to our workshop paper presentation. So in this presentation, I'm going to take you through the research that we have done, titled The Feature Representations of Transfer Learning and Gradient-Based Meta-Learning Techniques. My name is Mike Huisman, and this was a work in collaboration with Jan van Rijn and Aske Plaat. So let's get started. So nowadays, we're seeing deep learning algorithms achieving great successes in various areas and domains. However, as you can see in this plot, they require lots and lots of data to achieve such great levels of performance. So a natural question that arises is how can we build more data efficient deep learning algorithms? And in our research, we focus on two approaches to do this. So the first approach is the transfer approach. And the idea is that we have one large data set, which we use to learn or pre-train a given neural network. And then when we are presented with a new task consisting of maybe a limited amount of data, we reuse the learned network that we had, and we only fine-tune some of its parameters in order to learn this new task. Now, another approach which has been gaining a lot of attention recently is the meta-learning approach. And in the meta-learning approach, we are presented with different tasks, and the idea is that we want to distill some kind of prior that helps us to learn similar tasks more efficiently. All right, so we have, on one hand, we have the transfer approach, where the idea is really to reuse the pre-trained features that we have. And this often happens in two stages, namely the pre-training and then the fine-tuning stage. On the other hand, we have the meta-learning approach, where the idea is that we want to learn how to learn from just a few data. And common approaches to do this include, for example, mammal and reptile, which we will be investigating in our research. Now, a recent finding by Ragu et al. Shows that mammal mostly relies on reusing its features. And this may be surprising because that is actually what the transfer approach is also exploiting. We do, however, see some performance differences between the two because in some cases, mammal may be much more effective at learning new tasks, while in other cases, maybe fine-tuning works a bit better. So in our research, we want to investigate how the feature representations differ and how they relate to the few-shot learning performance. Now, one way to go about this question is to investigate the objective functions that each of these techniques is trying to optimize. Now, I will not go into the full details here, but fine-tuning really focuses on the initial performance, meaning the performance that it can achieve with the current set of neural network parameters. Now, mammal and reptile, on the other hand, are more look-ahead algorithms, meaning that they do not so much care about the initial neural network parameters, but more about the performance that we can achieve after making a number of update steps. And mammal is most extreme in this sense because it only focuses on the final performance, so after having made a certain number of T update steps. Now, reptile is a bit more in between fine-tuning and mammal, and that is because it tries to maximize the performance after every step of doing gradient descent. So it's a bit in between mammal and fine-tuning. Now, in the toy example, we try to investigate whether these three different objective functions actually also lead to different initialization parameters. And in this very synthetic and toy example, we have two tasks with two different loss functions. And as we can see, indeed, they learn different initializations. So for fine-tuning, we see that the learned initialization, which is close to zero, is there because the loss or the sum of the losses of the two tasks is minimum there. Now, mammal does something different because mammal positions itself close to the optimum of task 2 and a bit further away from the optimum of task 1. And the reason for this is that it realizes that it can still arrive at the optimum of task 2, while it can also arrive at the optimum of task 1 within the predefined number of update steps that it is allowed to make on these tasks. Now, as we can see, reptile is indeed in between fine-tuning and mammal, and in fact, it finds two different solutions depending on where we started off with the random initialization. Now, in a more realistic setting, we try to see if the few-shot learning ability of these algorithms relate to the broadness or diversity of their learned features. Now, what we mean by this broadness or diversity is what we measure or call the joint classification accuracy. And how we measure this joint classification accuracy is by taking the learned initialization parameters by each of these techniques. We freeze these initializations and we replace the output layer by a new one where every node corresponds to a test class that was never seen before during training. And then we try to fine-tune the initializations that we have in order to classify these unseen task classes. So in this way, we're really measuring, well, given the learned initializations that we have, how good of a job can we do at classifying these different classes. And in these different plots, we can see different things. So first of all, we see that in the within distribution settings, meaning that the algorithms are trained on tasks and evaluated on tasks from the same data set, we see that the performance there is, or the few-shot learning accuracy is much better than in the out of distribution setting, where they are trained on tasks from one data set and evaluated on tasks from another data set. Now, another thing that we find is that if we look at the most shallow backbone that we have investigated, which is the Cont4 backbone, we see that MAML yields the best few-shot learning performance. Another thing is that if we increase the depth of the backbone of MAML, we see that it actually learns narrower features instead of broader features. Moreover, we see that fine-tuning learns the most diverse set of features, meaning it has the highest joint classification accuracy in all of the settings. However, I have to add to this that this does not necessarily correlate to achieving better few-shot learning accuracy. So on this slide, we have summarized all of these findings that we have seen on the slide before. And with these findings, we hope to have shown a bit more light in this world of black box algorithms and how they exactly work. Now, if you have any questions about the research that we have done or maybe some suggestions, we would be happy to talk to you, and you can reach us by sending an email to the email address displayed on the screen. So with that, I would like to thank you for listening. And